Howdy, Chem fans! How's it going? It's day 79, the best year in Earth's history, by the way. What we're going to go after today is, of course, being able to explain how you can reduce the amount of acid you put into the environment, and then ultimately how to calculate pH so that a scientist, you in the future, could possibly know how to find out how much acid is in the environment. When we look at this, of course, one of the things that you can notice, look at that chubby little fella, is you should be able to explain something like this. How can an acid be both strong and dilute? And then give me 4 reasons, why an acid rain is really, really bad. Shouldn't be too hard, right? Normally would have been in the lab by now, but not this time, right? So stop me, write down the questions, draw and explain them, see if you can figure them out on your own. Hopefully you got some ideas. And we'll tackle these together, right? So we want to draw and explain how an acid can be both strong and dilute. My big ugly head's going to stick around this time. What I would want to do, though, is draw like a big beaker, right? And if we look at that big beaker, I could put an acid in it, but I want a strong acid. So hopefully your brain's like, I could go with stomach acid, like hydrochloric acid. And if we look at hydrochloric acid, they're not sharing equally. That chlorine is hogging most of the electrons, so it's very, very strong in its polarity, right? But if I want an acid, I got to throw that into water. So let's say that I got over here a nice liter of water, right? There's my water. If I throw this in here, I know that hydrochloric is a strong acid. How do I know it's a strong acid? Well, when I throw it in there, it should dissociate completely. It's going to rip completely apart, which is going to put the protons out there for every single one of the hydrochlorics. That's what makes it strong. It dissociates completely. We can think about it in terms of it's a good proton quarterback, right? You can almost write there. And the cool thing about it is it throws the balls like crazy. That's what makes it strong. However, if I look at this, that's going to put 1 proton in that whole liter of acid. So that's not a lot of protons to burn you, which means that this is not a whole lot of solute. This is a very dilute acid, which means that its concentration, which we've looked at before, its moles per liter of the hydrogen ions would be very, very low, right? Because that's at 1 liter of water. Now let's imagine, right, that I actually measure it, because that would be kind of handy. And I find out that its concentration is actually this. It's 0.0000001 moles per liter of hydrochloric, right? Which gets kind of ridiculous to write because there's all those zeros and they're just placeholders. So in science, we would just write it in scientific notation as 1 times 10 to the negative 7. Hey, that's easy to write. And that's for the molarity of the hydrochloric. And that's really all the hydrogens I care about with this stuff. Or I could say, hey, that's to the negative 7. That's a power. In French, that's pouvré, right? Oh, that's like the pH of 7, because there's not a lot of protons in there. That's what the P, of course, stands for. In French, it's pouvré de hydrogen. And in this case, of course, we can translate it in English. It is the power of hydrogen. And what we're talking about, of course, is the power of hydrogen ions. That's why we call it pH. And why it gives us that handy tool, right? So notice that an acid's strength is determined by its ability to dissociate. Its concentration determines, of course, how dangerous it really is. It's really a combination of those 2 factors. So if I have something that's strong and concentrated, you better watch out. That's battery acid. That's stomach acid too, right? It doesn't taste too good when it comes up the other end. Ooh. Now, more important topic. Why is acid rain bad, right? And if we look at this, the first thing that we should notice, of course, it rains all the time here in Washington. And if it's going to rain all the time and we have acid rain, would you want to pour acid from the sky? Well, you would get out of the rain if it did that, but there are lots of things that are stuck out there and can't do it in our evergreen state, and they're called plants. So one of the reasons why acid rain is so bad is it kills plants, right? This is because, of course, plants are standing out all day looking for this thing we mysteriously never see around here called the sun. And if we look at this, these plants, they have these leaves, and it's going to damage those leaves because you're spraying acid on all, of course, the proteins that make up their membranes, as well as the phospholipids. And if we look at this, that's a problem because for the plant, it's a solar panel, right? This is how they do the amazing thing called photosynthesis. So they can, of course, make sugar and make the world go around, as well as other things. But that's not the only thing that a leaf is. A leaf is actually the plant's lungs. Simplify it. It's their respiratory structure, right? So if we look at this plant, it's taking in this stuff that's killing our planet called CO2. It's good at doing that. It takes it in through these little holes called stoma. And it's letting out its waste product, which is called oxygen, which is kind of nice because you need that every moment of your life to survive. Now, let's imagine that I take that plant, and this is your lungs, and I have you open up your mouth and stare at the sky for a while, and we pour acid down your lungs. Your lungs are going to burn, and you're not going to be able to survive anymore. So what this means, of course, is this is going to mean no more photosynthesis for the plant, and without photosynthesis, you basically have dead plants, right? Now, why is that a concern? Well, if we consider the plants and the fact they make us oxygen, that's pretty handy of them, but they also have these beautiful things called roots. And as the water, of course, falls on it, if it's acidic water on their roots, it would kill their roots as well because the water flows underground and soaks into those things. And if you kill off the plant, well, it doesn't have roots to hold on to things like soil. So that's another feature of this, right? It's going to take the acid and get it out of the atmosphere and put it into the soil and what's in the soil, which is groundwater, right? They will also become acidic, and that will, hurt the plants in another way. No oxygen for you, no photosynthesis. The biggest part of that, too, is it also, of course, chemically reacts under the water and takes away all those wonderful things that are in the soil that the plants need, too, to build their things like chlorophyll. So this is going to do what's called leaching. It leaches the minerals, the good stuff, from the soil. This is stuff like phosphates and magnesium that they need to survive. Those are going to wash away downstream because they're being dissolved by the acid. That's what acid's good at doing as well, is breaking things apart with its charges. And that means more dead plants. Now, if you're not a plant fan or you really don't like groundwater that you drink every day, then consider this. This couldn't just happen to trees that purify our water for us. This also happens to other plants that we eat called, crops like corn. So this means things like corn and wheat. They're going to die because they're very sensitive to things like pH changes. And that's why we're going to see a decrease and are seeing a decrease in our productivity of farms. So less food for us and less oxygen and less safe water to drink. Wait, it gets better. After that, it drains downstream. Everything, goes with gravity here on Earth, down, down, down. And as it goes downstream, it makes its way into rivers and in the lakes. And then eventually it makes it out to the ocean, right? If we look at that, the thing that we should notice, don't want the screen's freaking out, but hey, we'll deal with it, is that would make those environments acidic. And being acidic, that would be a problem because what lives in them? Well, aquatic creatures like fish. Now, fish, of course, don't have lungs, but they breathe using these lovely, feathery, gentle things called gills. Now, once again, imagine if I take some acid and I pour it into your lungs. It's going to burn them, and you're not going to be able to breathe anymore, and you will suffocate, right? Oh, that could be a problem. So this burns the fish's gills and kills the fish. And that's a big deal because what relies on fish? Well, lots of ecosystems that tie together. In fact, it provides like 50% or more of the protein that humans eat. So that would explain why, almost 8 billion people would be running out of fish, besides the overfishing, all the fish are dying off as well as the other organisms that support the fish. Hey, that's a problem. And if you don't care about nature, food, or oxygen or any of these things, you can be like, hey, what about civilization? Well, most of our civilization comes from this awesome Roman idea of concrete. And concrete, of course, comes from things like limestone that we then grind up, squeeze, and chemically react to make this beautiful stuff called concrete. But basically, its base is calcium carbonate. Hey, it's a base. And that base makes up some parts of your teeth and your bones, right? It's calcium phosphate. But that's a concern because that means all of our buildings and all of our bridges and our roadways, those are built on concrete infrastructure. Oh, if it rains on them with acid rain, it dissolves them faster, and it would dissolve our infrastructure. And what have they been talking about? Well, they've been talking about for the last couple of decades how our infrastructure is crumbling and how we have to replace it now. And that means more taxes. So if you don't even care about nature that keeps you alive, you should realize that, you might care about the money that's going to go into trying to repair the effects of acid rain. And that's just some of them. Sounds like a great thing, right? I wonder why I kept my face today. Now, one of the things that we can also notice with this is you can see some of this if you've traveled to places like Europe where the Industrial Revolution has taken beautiful marble sculptures and the acid rain has literally eaten away at them so that they're dissolving. That's just a small example of this. That's why most true sculptures are now hidden inside of museums where the atmosphere that we breathe can't get to them. Oh, not a good idea. Or you go to the prettiest building I've ever seen. I don't really care about buildings, but this one was gorgeous. the Taj Mahal. It's built from white marble, and unfortunately, it's being eaten away because that lovely smog color is coming from all the traffic now that, the Indian population has enough money to buy cars, drive around, and all those factories. So that, of course, is eating away as they've increased their acidic rain as well as the areas around them. Then you guys are growing up on the West Coast. I didn't. I grew up on the East Coast, and this is what our forests look like in the Adirondacks. Hey, it's all dead. Why is it dead? Well, it's because we're downwind of you, but we'll get into that in a second. Unfortunately, the acid rain in my area was so tragic that it took out entire ecosystems of hillsides and poured into the lakes and rivers, which is why the trout weren't doing so good. Or the crops. Weird. Now, as that eventually drains its way down to the ocean, this creates a lot of dead zones where the fish basically burn their gills and then they suffocate, because a fish can drown too if it can't breathe. Oh. Now, normally you go up to the acid rain lab, take some of the big ideas and this text part of it. Today we're going to do that together. So get out your notes, and if we look at your notes, you can see that the big idea with the acid rain was where on your graphs, because you would have graphed out the CO2 and the SO2, how that affected the pH of the water, and explain the difference. So I'm going to do that for you. If we look at CO2, when we bubble that into it, it makes carbonic acid. And carbonic acid is a weak acid. It does not dissociate completely. So you can see that when it does that, it actually drops the pH a bit, right? That, of course, lowers it down below 7, but it's not a super strong acid, thankfully, because otherwise everything on Earth would be dead right now. But it still burns it to some effect, right? If we do it with the SO2, you bubble that in, that makes sulfuric acid, and sulfuric acid is a stronger acid. It's got 2 protons to it. That drops the pH very, very quickly. And that's why things like the exhaust from coal-burning plants is even worse than just coming out of your car with CO2 or you breathing. That, of course, makes for a worse acid rain. Now imagine you combine the two together, or you put a high concentration of CO2 in, you're going to have even a weak acid becoming really, really strong. If we look at the last part of the experiment, that's where you put in some acid, the pH drops. Then you drop in some calcium carbonate, some concrete, some limestone. That causes the pH to rise a bit, but not completely. It still stays acidic with the amount that you put in. And then you put in more squirts of acid. And it went acidic, it dropped in its pH, and then it went up a little bit less acidic because you put in a base, and then you drop in the acid and it goes a little bit down, but it stays level. Even though you're adding more acid, what this calcium carbonate is doing is it's acting as a buffer. It's a substance that helps to stabilize the pH. And you use buffers in your body, and they use them in the ocean, which we'll see in just a moment, right? So what are some sources of acid rain? Well, one of the biggest sources is this thing called SO2. And SO2, sulfur dioxide, comes from, you can see a map here of sulfate concentrations throughout the United States, which give you an idea of the sulfur dioxide levels. You can see that there's a big problem with it out here, but that's because there's all these lovely, iron and steel mills and factories that are producing the steel as well as cars out in this area called the Midwest. And that means that if you look at the folks where I was, all the power plants to run all those things by burning lots of coal like they do on the East Coast especially, and throughout the West Coast, they all kind of funnel with this thing called the jet stream straight towards where I grew up in New York, upstate New York. And that's why the pH, of course, is such a horrible thing in this area, because we get the loads of everybody upwind of us. Now, you'll also notice that it's not completely zero over here in Washington. Even though a lot of our electricity comes from things like hydroelectric, we still have plants, and the wind shifts from things like California or all the way across the ocean in China, where all those materials you buy, they're burning coal to do that because it's the cheapest way to do it. Floats across, and this is increasing steadily, right? So that's mostly from power plants and coal burning. Then you add in these things called nitrates and nitrites. We can see that it's a big hit in the Midwest. New York is horrible, as well as the East Coast is far higher than, say, Washington. And that comes from the fact that there's a lot of agriculture here. But if you look, it's like a funnel all the way from the West Coast cities. That's because things like nitrates and nitrous oxide, they come from the inefficient burning of fuels inside of our cars. So car exhaust is the main extent of that. You can basically see the downwind pattern of the jet stream coming from places like LA and Phoenix as it then builds in more and more cities. We are only lucky here in Washington because ours gets carried down to hit all the rest of the folks on the East Coast. Thanks for that. And we've got this giant ocean in front of us, so there's not that many cars driving in front of us at a close proximity. There's still far more on the other side of the ocean, right? Then, of course, if we look at pH, it's the biggest indicator of it. You can see that the pH of places like the East Coast is much, much lower than the West Coast. And it follows the same pattern. The pH is affected by combustion and power plants as well as automobiles. And that's the downwind effect. That's why the forest where I grew up were all dying from pHs of like 4.3, which is really, really low. And all the fish were dying. Now, it seems like it's fairly good here, but you can see that this is even outdated data. It's even lower than it shows right here now because China's been buying cars and they've been building a lot of iPhones and sneakers, and that's now showing up, and they can tell by the isotope signal in the CO2 concentrations as well as the sulfur dioxide. Oh, the acid rain that's acidifying our environment. So all those lovely evergreen forests, I hope they stay that way. Now, the problem with this is that the CO2 that comes out of these things is invisible. Even if you see the exhaust of a car, you're just seeing the water vapor that's condensing. But this is an invention to pump up your car based on it, and it fills up in just a few minutes. So your car puts out tons and tons of this every single year. So does mine. So in terms of figuring out why that's a problem, let's imagine that there were like close to 8 billion people. We're getting there. And a lot of them are driving vehicles now or running on electricity. We've put a tremendous amount of CO2 in the atmosphere. And as Le Chatelier tells you, if you add, it moves away. So it pushes into the ocean. As it does that, it goes into solution. It becomes this stuff called carbonic acid. That's CO2 mixed with water. There's my carbonic acid. It's a weak acid, but it's an acid, so it dissociates, donates a proton, right? And that proton can be a problem, but it also makes these things called bicarbonate ions. Now, we've pushed in so much CO2 that now these bicarbonate ions are also dissociating because the pH is changing so much, and they dissociate into the hydrogen ions and the carbonate ions. And that means that as we do that, well, there's more protons, so those protons then bump into the carbonate ions in the ocean and turn them back into this thing called a buffer, a bicarbonate ion. So to buffer the ocean and have those hydrogens bang into those, that uses up the ocean's carbonate ions. That's a big deal because the only place you can get those carbonate ions from is from the water, which is a low concentration, and from the sea life. So as we put these protons in from all of our CO2, we acidify the ocean, which means that these protons have to be gobbled up by the new receiver, which is the carbonate. So the ocean runs out of carbonate ions, and things like sea life that live in shells, mollusks, corals, they lose out because this basically dissolves them. Now, when we look at that, what that means in a simpler picture is this is what the reefs looked like when I was a kid, good 30 years ago when I started scuba diving. And this is what they now look like as we push to 500 parts per million of CO2 like we are globally. Unfortunately, reefs are dying out. And you'll also notice without the reef, you don't see the fish because that's their home. And if we look at that, that's been the story worldwide. We can see that there is, of course, an indirect relationship. As, of course, the CO2 increases, the pH decreases. And look, it's going exponential. 1950s reefs were looking really, really healthy, but man, we burned a whole lot of coal and a whole lot of gasoline since then. This is a previous prediction, but it's being confirmed. We're now losing coral reefs at a rate of about 70% are showing severe damage or completely dead, and it's likely by the next 10 to 20 years that they'll all be gone if this trend continues. Now, what's scary about that is that in the ocean, there are these things that are called the potato chip of the sea. They're known as fairy snails. Most people never heard of them because they live in the deep ocean. But if you live in the ocean, you know about fairy snails because they make up a huge part of the food web. They are one of the snack chips. They're the thing that everything eats in the ocean. Because who doesn't like potato chips? Well, that's what they are. These swimming snails, because they have these wings that make them look like little fairies and they swim around, they unfortunately are dropping drastically in their numbers because as the pH of the ocean decreases, the hydrogen ions are eating away at their calcium carbonate so that as larvae, they don't form and they sink because they can't be buoyant and they die. And if you cut out the base of the food chain, which is what these fairy snails are very much a huge part of, you don't have the shrimp that eat them or the fish that eat them or the large sharks and large whales that are so beautiful or all the tuna and salmon that we so love to eat as humans. It's almost like this would mess up the food chain that supplies the food for the top predator. And when you chop off the bottom of the pyramid here, it falls over. Oh, no wonder fish stocks are dropping. Well, that's not good. said, that's more than 50% of human protein comes from it. Now, that's a worrying pattern when we look at where the pH has dropped the most. You can see that in the oranger areas, that's where the pH has had the most drastic drops. That's where it's becoming the most acidic. And look where it is. It's off the East Coast, off the West Coast, but it's mainly in the cold oceans. And that's a huge concern because we don't have coral reefs around here, but most fish that humans eat, the huge populations of fish, that's in the cold oceans, and they're getting hit with the biggest pH changes. So, in the tropics, losing the coral reefs, that's where 70% of the fish start their life off. In, of course, the cold regions, that's where 90% of the fish we eat come from. They're being fried as larvae, or they're starving to death because the food chain is disrupted by all the invertebrates, all the things with shells being eaten away. Not really good info, but true. This humorous but sad cartoon shows the basic idea of the richness of life greatly decreasing in our food supply, going with it as the pH drops. And of course, most people unfortunately think, oh, the pH is dropping, that's good. If it goes up, it's bad. No, a pH drop means it's becoming more acidic. If you want more information on that and some visuals on it, there's this thing that'll bring a tear to your eye called Chasing Coral. You should check it out on Netflix. I do not advertise for them, but it's a good documentary and quite informative to see what's going on. Now, the really scary news. For a long time, the folks in China throughout the 50s and 60s, they were riding bicycles because they were poor and they had to ride their way to the farm or the factory. But then we Western societies started buying lots and lots of gizmos that say made in China. Think of your iPhone. Think of any toy you've ever had. Think of any floaty like I just built up a pool, right? That made in China thing is, well, because there's factories that are burning mainly coal to do that. And by building stuff for us and us buying it like crazy because we're massively in debt to them, they now have enough money from all those jobs at factories that they want the dream that we've been living, the comfort of a car and transport. And that means even more combustion. So now you don't see the bikes like you used to see. You see cars like on American highways. And this is Beijing on an average day. This is the smog from all the car and the factory exhaust. They shut it down during the Olympics so that people wouldn't notice how bad it was. But people actually wear masks outside, and the acid rain from that is abominable. Now, combine that all together with the acidification of our environment, which is what's going on. China is now growing and booming to be, with 1 billion people, far more impactful than just us alone. And it's not the them and us, it's us combined, all of us, right? So if we look at this, there's got to be some options to help with this. Well, chemistry to the rescue. You can, of course, some people are like, well, the ocean's becoming acidic. Let's throw in a buffer and neutralize it. That, unfortunately, is what the coral reefs are doing. They're buffering the pH change and trying to stabilize it because just by Le Chatelier, hey, I got too many protons. Oh, I got to gobble them up and add them together to make bicarbonates. It's likely that we could not, as humans, add enough buffer in the correct way to actually stabilize the pH. If we did, we need some people that really understand chemistry, which is why we're doing this. The other idea, of course, is the calcium carbonate. We have a lot of limestone on Earth because those are ancient reefs. Some people say grind it up, stick it into the ocean. Chances of getting that right, very, very slim. You'd likely end up with too basic an environment in the one area and kill all the fish in that area. So need a better option, more like cut it off at the source. One option for this idea is clean coal. There is no clean coal at all. All burning of coal makes CO2. But especially dirty, cheap coal, it produces a lot of sulfur dioxide. So if we look at that, that comes out, and as it goes into the atmosphere, makes the sulfuric, and that makes the more acidic environment even more dramatically, right? So one of the idea was to take this scrubbing idea, and basically they spray a bunch of sprinklers, which put the SO2 into solution, then they drain that off, and then they break that away and sludge it so it doesn't go into the atmosphere and spread further from it. A nice option. The only problem is it's more expensive. So that means you have to pay more for your electric bill, right? So in terms of practical solutions on the fixing on the back end, not a lot of them. That means that's to come on the front end. And that's where we have to reduce our acid rain. How could you do that? Some obvious ones. Motor vehicles are one of the biggest producers. So you could ride your bike more. Probably not going to happen. So you could, of course, carpool. That means riding with your friends and family wherever you need to go, to practice, to school, in a normal school when it's not remote. Hey, this remote thing is greatly helping the CO2 levels, but that'll change when we all get released to drive wherever we want again. The ultimate carpool of all, of course, is called this thing called the school bus that we see lots of them driving empty because it ain't cool to ride the school bus. But many of you will go off to college soon, and in places like Seattle and Bellevue, there is a great infrastructure for public transport, and light rail could bring the option. So the more those are supported and used, which is the way you support them, the more money they make, the more likely it is to have less production. That means that everybody in that load shares that carbon emission, which reduces it for each one of you, right? More efficient transport. But the biggest thing of all has to come down with this thing. It's not just about the electricity you use, which is a huge producer, or the amount you drive. It's also about the energy that's used to produce the stuff that you buy. You should probably check out this thing called The Story of Stuff, or take a look at your brand new phone and realize that that came from a place like China, where it was built using coal, the dirtiest methods and cheapest, to keep the cost down so that you could buy it. The truth is, the more stuff you buy, the faster the planet dies, right? Now, one of the things that we can notice with that is I can mention that because every piece of clothing that I wear is hand-me-down clothing. I go to places like Goodwill so that I can use reused clothes that doesn't have to go to a factory or a plant. Again, it already made its emission. I don't need to make a new one. The TV that's behind my head is a second-hand TV. It was borrowed from a friend. I don't buy new things as much as I can because that means that I'm not putting more CO2 in the atmosphere. Now, along with that, other things that I do, I have to use electricity. I'm doing it in my home right now to do this. I actually pay extra every single month. The PSE, the Puget Sound Energy, has a wonderful program called the Green Power Program, where you can elect to have all of your energy if you pay an extra. Mine's about $15 to $20 extra, depending on the month, that I pay additional so that all of my energy comes from renewable resources. You can pay even more if you want it to come all from solar, which is an awesome option in our area, especially since we have hydroelectric that can make that possible. It's a cheap way if you can't afford putting solar panels on your house, or you can't figure out to turn off the light switch when you're not in a room, right? Included with that, of course, if you use secondhand goods, that means they don't have to be produced and shipped across the giant ocean and all the CO2 that it floats on. That means there's a greater chance that maybe, the future will have things like this. Now, I've been lucky in my lifetime to see some of the most beautiful coral reefs on Earth. And they are the most wonderful, being a bio nut, things on the planet. If we don't make the change, one, you'll never get to see them because they'll end up doing what about 70% of the reefs on Earth are doing right now because no one is doing anything about this. They're just consuming. And if you don't care about nature, then maybe you'll care about people. There's a reason why parts of Africa, South America, parts of the United States, parts of Central America, the whole world is starving. It's because a lot of them base their protein diet on things like fish. And without coral reefs, which are the nurseries of the sea, you can't have the fish to feed the people. And yet, you try explaining why you needed your new phone to this kid when he just needed a meal, right? Now, normally we'd take a break this time to reflect on that, but I don't get to do that. Maybe you get to. You can pause me, but hey, it's time for some notes of how a scientist would actually measure and prove all this stuff to a government official so that the government official could forget about it. Or they could, try to fix it. That could be you. So if we look at this, there are these things called logs. And a lot of kids don't really like them or get them. But the cool thing about logs is they basically do this. I got a number, 1 times 10 to the negative 2. I can take it and turn it into regular notation of 0.01. That means there's 2 jumps to the left, right? It's a small number. Or I could say and take a log. If I take the log of 0.01 base 10, that's negative 2. So really what the log is doing is it's telling you the power of the exponent. That's really handy when you have really little numbers, which is what we run into when we're dealing with things like pH. So cool things about this. I'm going to get rid of my head now. If I look at the formulas that you need to know, you should write these down. You can pause it right now and take a look at it. These are the 6 formulas that you absolutely need to memorize and be able to use so you can understand how to work with pH. There's this thing called kW. I'll explain all these in a second. It's 1 times 10 to the negative 14th. And that's equal to the hydrogen ion concentration times the hydroxide concentration. Then pH, the power of hydrogen. If you want to find that, it's the negative log of the hydrogen concentration. Don't forget the brackets, that's moles per liter. If I want to get to the hydrogen concentration, I can simply use the power of hydrogen as the exponential power, a negative pH to the base 10 there. So 10 to the negative pH, and I get it. Then there's this thing called POH. Hey, it's the power of the hydroxide. That's the negative log of the hydroxide concentration. The concentration of OH would be 10 to the negative of the POH. And if we put the pH plus the POH, you get exactly 14. It's really convenient. So let's dig into these a little bit deeper. Write this down. The pH scale goes from 0 to 14. Anything below 7 is acidic. Anything above 7 is basic. We already know that one. It's the power of hydrogen, right? That's all based on a thing called Kw. It's the constant of water. When we put water with water, it dissociates, and it makes exactly 1 times 10 to the negative 7 and 1 times 10 to the negative 7 of the hydrogen ions and the hydroxide ions, which combine together to make, to the negative 14th. That's why it's a 14th scale, right? If we look at the pH, if I need to pee, I pee on a log. That's how I remember it. I take the negative log of the hydrogen concentration, which is pretty easy to find and calculate. Or let's say that I need the hydrogen ion concentration. Well, I don't need to pee because I got to pee. So I use my P as a power. 10 to the negative pH gives me the hydrogen concentration. The cool thing is what works for the H's will work for the OH's in a very similar fashion. So if you need to pee, H, pee on a log. That's how I remember it. If you don't need to pee, use it as a power, right? With POH, it is the exact opposite scale, and it's totally new to you. It's not as famous, but it is used in science, and it's used for your problems that you're going to face. It is flipped backwards so that it's a 0 to 14, but anything below 7 on the POH is basic. Anything above 7 is acidic. I know, it's annoying, but that's the way it works, right? Now, if I need to pee, I still pee on a log. I take the negative log of the hydroxide concentration. If I need the hydroxide concentration, then I use my P as a power, 10 to the negative POH. And the really cool thing about it is if you put the pH and POH together, you'll get 14, which means if you know one, you can find the other with some very simple math. Now, let's see what you're going to use this for. Make sure you know these formulas. They are the handy ones, right? I want you to write down these questions and then try to calculate them. I will give you a hint. It usually takes more than one step, right? So write them down. Hey, human blood, sweet. Cool. Let's tackle those together because I'm starting to run out of voice. If I want to calculate the pH of a solution where the hydroxide concentration is this, well, then I'm going to need some steps. Ultimately, what I need is I got to figure out what I got and what I need. I need pH, and what I got is the hydroxide concentration. So first step of this, here's what I'm going to do. There's many ways to solve these. I'm going to realize there's this thing called Kw, where you look at the hydrogen and the hydroxide concentrations. That is always equal to 1 times 10 to the negative 14th because of water. I need to know the hydrogen concentration so I can get to the pH, and I know that the hydroxide is 10 to the negative 6. Then I can solve for the hydrogen concentration, which is 1 times 10 to the negative 8. Hey, that negative 8 is important, right? That's a little number. Now that I have that, well, I need a P, so I'm going to P on a log. I'm going to use the pH is equal to the negative log of the hydrogen concentration. When I do that, I can just plug it in. I put in the number in scientific notation. I take the negative log, and it's easy because, of course, it's base 10, so it's really just the exponent. That's going to be the pH of the negative 8, which comes out to a pH of 8.0. 2 siggy figgies because we're going to take it easy on it. It's not the exact siggy figgy rules, but we'll just keep it that way, right? So your head doesn't explode. Now, what does this mean? The cool thing is that means when I look at a number for concentration, I only really look at the exponent because that basically tells me the pH, right? And when I do that, I can see this 8.0. Well, 8.0 is above 7 on the pH scale, so that's a little basic. Hey, that's a little basic. And that makes sense because at 1 times 10 to the negative 7 is neutral. That's why 7 is neutral. This is negative 6, so that's a little bit bigger. That's times the power of 10 for the hydroxides. There's a little more hydroxides than there are H's. Oh, it should be a little basic. So always can double check. Last one for today. If we look at this, it's got once upon the pH. So I need the pH, or I've got the pH is 7.4, and I need the hydroxide concentration of human blood, right? So first step that I can do for this, I can use my pH plus POH is equal to 14.0. Well, that's easy. I just plug it in and follow my math rules, and I can subtract that away, and that means the remainder is 6.6. That's now my POH. Well, I want to find out the OH. Well, I got the P, so I don't need a log. I can use it as a power. 10 to the negative POH. I plug in my 6.6 that I just found, and boom, it tells you that it's 2.51 times 10 to the negative 7. Now, if we look at that, I'm going to get siggy with it. It started with 2 siggy figgies, so we're going to make it easy on you, and it's 2 siggy figgies. It's 2.5 times 10 to the negative 7, right? Now, does that number make sense? Well, to the negative 7 in a hydroxide concentration would be neutral, but I got 2.5, which means it's a little bit more than 1 times 10 to the negative 7. So it's a little more hydroxides. And if I look at that, hey, look at that. It's a little bit higher than a pH of 7, so it's a little basic, and that's a little basic. You're going to be trying some of those this week. What I did want to show you is something to remember. If you need a pH, P on a log, right? If you need a P, P on a log. Log it. If you've got the P, use it as a power to get to the actual hydrogen concentration. And whatever works for the H works for OH2, right? If you need a P, P on a log. If you got a P, use it as a power, right? Now I wanted to show you this because it's pretty cool and it's got vomit in it. So let's take a look at that. This is a great FET that you can explore on your own as well. As you go into it, you can see that it's got this right here, and it's got this lovely stuff called water. The neat thing is it can show you the particles. The red ones are the hydroniums. Those are hydrogen ions grabbed onto a water, right? That's the burning part. And then there's the OHs, which are the hydroxides, the other half of the water. You can see this is water with a pH of 7, so it's got a concentration, hey, of 1 times 10 to the negative 7 for each. They're perfectly neutralizing each other. Now, the neat thing about this is I can also look at the molecule count. Tells me how many are there. Now, as I do that, one of the cool things I can do is I can increase one or the other. Hey, I just made it basic. And when I did that, this went to negative 6 and that went to negative 9. Hey, that always comes out to negative 14 if you actually combine them by multiplying. Oh, it's neutralized. Or I want to make it acidic. If I do that, I need to increase the amount of hydrogen ions, hydroniums. And look at that, to the negative 4 to the negative 11, and I put in the first part and it would balance it out, right? So hopefully you recognize that these numbers are not just fictitious things that were created. It's because at 10 to the negative 7 of each of those, that would equal the right number of waters to be 1 times 10 to the negative 14th, right? Neat thing about that is then you can go in and list, and you can see that's water, but you can also use vomit, right? And here's vomit. Why does vomit burn your throat? Well, because there's a 10 to the negative 2. That's a lot of hydrogen ions and very few hydroxides. That's why it's acidic. Or you can take something like some coffee. Oh, that's why I don't drink coffee, because it's to the negative 5th. That's like a pH of 5. Oh, it's acidic. So look at the exponents for the hydrogens. That tells you what it is. Or even better, hey, some soda pop. That's to the negative 3rd. Oh, but it's 3.2, so it's 2.5. That's really acidic. Oh, no wonder my dentist doesn't like me because I don't drink it, right? Hey, a battery acid. Ooh, to the negative 1. That's a lot of hydrogens, right? Oh, hope that helps it to make sense for you. Our target normally would be able to figure out how you could reduce your acid rain or your acidification of the environment. And you should definitely watch this Chasing Coral thing. Biggest thing that you could do to help us all, carpool and stop buying so much stuff. I'm trying to do my part. I reuse, reduce. The recycling is not as good because it still takes energy to do that. With the other part was calculating pH. If you need, of course, calculate the pH. If I need a P on a log, I use the negative log of the hydrogen concentration. If I have the pH, then I can use that as a power. 10 to the negative pH will give you the hydrogen concentration. And whatever works for the H's will work for the OH's. Woohoo! Oh, look at that reef. Should have been nice if they still existed when, you could afford to go to them, or when my kids are old enough to enjoy them. That'd be cool.